Good evening, everyone. This is the discussion session, problem solving discussion session, the last session of the online course Soil Mechanics Geotechnical Engineering 1. All the 12 sessions have been completed just yesterday, and this is an extra session, summary session of 1 hour, in which I would be just going through some critical questions, some very important questions uh, which have been already covered, which are major conceptual parts of the important chapters of this course. Okay, so it's already 4. Without further ado, I just go to the PPT. I hope the PowerPoint screen is visible. Okay, so I will start the discussion class now. There are approximately 15 questions. There are, I think, yes, there are 15 questions. I will discuss the questions right away because this is a session of 1 hour. So I'll be discussing the solutions to the questions right away. Okay. All right. So the first question here is, what is the type of soil formed after deposition in lake water? What is the type of soil formed after deposition in lake water? The options are alluvial soil, lacustrine soil, colluvial soil, or marine soil. The answer of this question is lacustrine soil. Alluvial soil are formed by deposition from the river water. Colluvial soil due to gravity. Sorry. And marine soil due to deposition from the sea water or the sea rather. Okay. So lacustrine soil is formed after deposition in the lake water. It is called lacustrine soil. This is an important question from the first unit, origin of soil and its formation. Okay. The next question is, which of the following type of soil remain at their place of formation? That means they are not transported from one place to the other. They remain at their place of formation. It is a very easy question. The answer is residual soil. The answer to this question is residual soil. They remain at their place of formation. Others, they are transported. For example, aeolian soil transported by wind. Marine soil, I have mentioned the previous question also, by the sea. Colluvial soil, again, transported by the action of gravity. By the action of gravity. So, which of the following type of soil remain at their place of formation? The answer is residual soil. Residual soil is a type of soil that remain at their place of formation. Okay. Now, next question. Yes, this is the soil classification part. The biggest size of clay particle is. The biggest size of clay particle is. The answer is 0.002 mm. This is also equal to 2 micron. 2 micron. This is the largest size of clay particle. If we have a soil particle beyond this size, larger than this size, it will be silty soil up till a size of 75 micron. Beyond that, fine grain sand will start up to 4.75, beyond which it will be gravels. Okay. beyond which it will be gravels. So the biggest size of clay particle is 2 micron. Any particle size of soil below 2 micron is a clay soil, is a clay particle. I hope it was clear. Next question. Silty clay indicates, yes, this nomenclature, silty clay, what does it indicate? When we write at first silty, that means the first word describes the second word. It's an adjective. That means the major part is the second one, is clay. So it is actually a clayey soil containing some percentage of silt, or silt percentage is less than that of clay. It is called silty clay. It is called silty clay. Silt percentage less than that of clay. It's called silty clay. Okay. I hope it was clear. Next question. Among the given soils, the specific surface is the highest for. The specific surface is the highest for. Just a moment. Yes. So what is specific surface? Specific surface is defined as surface area per unit mass. Surface area per unit mass. Now for a given mass of soil, in the options we have sand, silt, gravel and clay. We know based on the particle size, gravel has the largest particle size, then comes sand, then comes silt, then comes clay. Okay, I'll write mass like this because M is silt. Gravel, sand, silt and clay. So for a given mass of soil, which of this type of soil will have the largest number of particles? Obviously clay. Clay will have the largest number of particles, most particles, because it is having the least size. So for the given mass, it needs more number of particles to fulfill the requirement of mass. So most particles will be in clay. The more the number of particles, the more is the surface area. The more is the surface area. So surface area per unit mass will be the highest for clay, and hence the specific surface is the highest for clay. Per unit mass, clay will have the most number of particles, hence it will have the most surface area, the highest magnitude of surface area, and so it will have the maximum value for specific surface. Okay. I hope it was clear. And yes, the specific surface will be the lowest for which particle size? For gravel, because for a given mass it will have the least number of particles. The least number of particles. Okay. I hope it was clear. Next question. Yes. So a soil has liquid limit of 20% and plastic limit of 14%. As per IS classification, the soil is, the options are inorganic silts with high plasticity, organic clays of medium to high plasticity, inorganic clays and silts of low plasticity, inorganic clays of medium plasticity. So the soil can be organic or inorganic, can be clay and or silt. It can be a soil of high plasticity or a soil of low plasticity. Plasticity means the compressibility of the soil. Now we are going to solve this question using this plasticity chart as per the IS classification system. So here you can see in the x-axis we have the liquid limit, on the y-axis we have the plasticity index, and we have a line called the A line, the equation for which is given over here. This A line, it separates the soil of high plasticity, intermediate plasticity, low plasticity, with the help of these two vertical lines. And this line, this A line specifically, it segregates two types of soil mainly. The upper part, it mainly has clay, and the lower part is mainly has silt. M is silt, O is organic soil. So the lower part has silt and organic soil, the upper part has clay and inorganic soil. Okay, now this H, I and L, what does it mean? H means high plasticity, I means intermediate plasticity, and L means low plasticity. So these two vertical lines representing liquid limit of 35 and liquid limit of 50 is dividing the graph into their plasticity zones. Okay, beyond the liquid limit 50, as you can see, we have the soils of high plasticity. Between the liquid limit of 35 to 50, we have the soil of intermediate plasticity, and below liquid limit 35, we have the soil of low plasticity. Okay, except this region which is shaded, it has clayey soil and silty soil of low plasticity, and this region, it extends from plasticity index of 4 till a plasticity, I'll just write it like this, plasticity index of 4 till plasticity index of 7. Okay, so I think the graph is clear. Now I'll go back to the question. Here we have been said that soil has a liquid limit of 20%. So liquid limit is 20, plastic limit is 14. And what is the plasticity index? IP, the value is liquid limit minus the plastic limit. 20 minus 14 gives us 6. Plasticity index is 6. Okay. Now we'll go to the graph and see where does it fall. So liquid limit of 20, and plasticity index of 6. So first liquid limit 20, that means this vertical line, okay, and plasticity index of 6. That means along the vertical line between 4 and 7, that means it is lying in this zone. It is lying in this shaded zone. Okay. And what do we have in the shaded zone? What do we have in the shaded zone? We have inorganic. We have inorganic soil because it is above the A line, so it is inorganic. Here we have C and M, that is clay and silt, both, and we have L, that is low plasticity. So because it is above the A line, the soil is inorganic, having clay and silt of low plasticity. Which option it will match? Option number 3, as you can see, inorganic, clays and silt of low plasticity. Inorganic clays and silt of low plasticity. Okay. Is it clear? Okay. I'll go to the next question now. Yes, inorganic clays and silt of low plasticity. Okay. Yes. A soil has a liquid limit of 30. The corresponding plasticity index given by the A line is, what is the A line? A line is a line separating the organic soil from the inorganic soil in the plasticity chart. What is the equation? The equation of the A line is IP, that is plasticity index, equal to 0.73 into liquid limit minus 20. So I'll write here like this. According to the A line, the plasticity index in the A line IP as per the A line, it is equal to 0.73 liquid limit minus 20. So what is the liquid limit? It is 30 minus 20 is 10. We get a value of 0.73 into 10, it is 7.3. That is 7.3. So whenever we will be asked to find the plasticity index by the A line, it is a boundary condition between the organic and the inorganic soil. Okay, organic and the inorganic soil, and also silty and clayey soil. Silty and clayey soil. Only this shaded region has both silt and clay. Otherwise, the A line also differentiate between clay and silt and between inorganic and organic soil. Okay. So this line gives the plasticity index as per the equation IP equal to 0.73 into WL minus 20. Here WL, there is a liquid limit is 30%. We get a value of the plasticity index as 7.3 given by the A line. Okay. Next question. The maximum water content at which a reduction in water content will not cause a decrease in the volume of soil mass. In this question also, we have given a graph over here. We can see the water content is in the x-axis, the volume of soil mass is on the y-axis. Now initially, as we proceed from right to left, from A to B and then to C, the soil has so much water in it that it is practically in liquid state. Okay, in this. As we reduce the moisture content, the soil transitions from liquid state to a plastic state. So this liquid limit is that percentage of moisture in the soil beyond which the soil will practically behave as a liquid. Okay. Now this zone, liquid limit and plastic limit, which we call it as a plasticity index, is a zone in which the soil will be in a plastic state. It is highly deformable stage. Below the plastic limit, the soil will be in a semi-solid or stiff state until we reach the shrinkage limit Ws, below which there will be no change in the volume. As you can see, the shrinkage limit is at the point B in the graph. Below the shrinkage limit up till the point C, there is no change in the volume. Even when we decrease the water in the soil, we reduce the moisture content in the soil, there is no change in the volume. So this moisture percentage below which there is no change in the volume, even if the water is reduced from the soil, is called the shrinkage limit. In other words, we can say the maximum water content at which any reduction in moisture, so this is the maximum moisture content. This is the maximum moisture content. If we go beyond this, then if we reduce the water content, the volume will change. But this is the maximum moisture content at which, from this point, if you reduce the moisture content, there will be no change in the volume, no decrement in the volume. So this point is called the shrinkage limit. So again, the maximum water content at which a reduction in water content will not cause a decrease in the volume of soil mass is called shrinkage limit. It is called the shrinkage limit. Okay. I hope it was clear. Next question. Sorry. A soil mass compacted at a moisture content of 12% has a bulk unit weight of 18.73 kilonewton per meter cube. Its dry unit weight in kilonewton per meter cube is 15.98, 21.34, 15.87, 16.72. So in this case, we have the bulk unit weight given. Okay, bulk unit weight given and the moisture content given. Now we have to find out the dry unit weight. Now first of all, what is bulk unit weight and what is dry unit weight? Bulk unit weight is mass by total volume and dry unit weight is mass of the dry soil by total volume. If we divide the mass of the dry soil divided by the volume of soil solids, we get the unit weight of soil solids. Here I am talking about dry unit weight. So mass of the dry soil divided by total volume, and bulk unit weight is mass of the total mass of the soil, that is in its partially saturated state, whatever we find out. Mass by volume is a bulk unit weight. So how do you find out dry unit weight from bulk unit weight? So here gamma T, suppose it is the bulk unit weight, it is given as 18.73. Okay, and this moisture content W, it is given as 12%. In fraction I will write as 0.12. Now dry unit weight gamma D is equal to the ratio of bulk unit weight, this is gamma T, and 1 plus the moisture content. Now we solve this. So 18.73 divided by 1.12. We get a value of approximately 16.72. Which is option number 4. So in this question we have been given the bulk unit weight and the moisture content. We can find out the dry unit weight using the formula gamma D, that is dry unit weight equal to gamma T, bulk unit weight divided by 1 plus moisture content in fraction. Okay. In a similar way, dry density and bulk density will have the same relation. Dry density equal to bulk density divided by 1 plus the moisture content in fraction. I hope the solution is clear. I go to the next question. In a wet soil mass, air occupies 1/6 of its volume and water occupies 1/3 of its volume. The void ratio of the soil is. The options are 0.25, 1, 0.5 or 1.25. As we know, the void ratio can be less than 1 and can be more than 1 also, because the void ratio means the volume of void divided by the volume of soil solids. So in this case, let us assume that the volume of the soil V is equals to 1 first. V equals to 1. Okay. Now we have been told that air occupies 1/6 of its volume. That means volume of the air is 1/6 of V. That is 1/6 of 1, that is 1 by 6. And water occupies 1/3 of its volume. Again 1/3 of 1, that is 1 by 3. Now it is a wet soil mass. So the pores in the soil will be filled up by water and by air also. If it was fully saturated, then the pores, the voids would have been filled up by only water. Now we can assume that it is a wet soil mass. Since air is there, it is a partially saturated soil mass. The void will have both air and water in it. So the volume of void, so all the voids, the entire void in the soil is filled up by either air or water. So the volume of void in the soil is equal to the volume of air plus the volume of water, that is equal to 1 by 6 plus 1 by 3. That gives us half, isn't it? Volume of voids is equal to the volume of air plus the volume of water. Okay. So 1 by 6 plus 1 by 3 gives us half. Now the volume of soil solids. What is the volume of soil solids? A soil has solid particles and voids, isn't it? So the volume of soil solid will be equal to the total volume of the soil minus the volume of voids. The total soil volume, if we subtract the volume of voids from the total volume, we get the volume of the soil solids, and that is equal to how much? It will be, what is V? V equal to 1 minus VV equal to half. We get again half. We get half. Now we go for the void ratio. We have found out the volume of void. It is equals to half. And the volume of soil solid is also equals to half. Okay. Now we go for the void ratio, that is E void ratio equal to volume of the voids divided by volume of soil solids. Now both are equal, volume of voids and volume of soil solids both are half, so we get a value of 1. So the void ratio of the soil is equal to 1. Okay, so first of all we just write down the volume of air and volume of water in terms of the volume of the soil mass, total volume of soil mass. Next, we find out the volume of the void by adding up the volume of air and volume of water. Then we find out the volume of the soil solids by subtracting the volume of void from the total volume of soil mass. And then the volume of voids divided by the volume of soil solids gives us the void ratio, which in this case is equal to 1. Is equal to 1. Okay. I hope the solution was clear. I'll go to the next question. A particle size distribution curve with a flat portion represents. A particle size distribution curve with a flat portion represents. The options are uniformly graded soil, well graded soil, gap graded soil, or poorly graded soil. Now, uniformly graded and poorly graded both are similar. That means a certain it is graded in such a way that many particle size, they are absent or they are not present in the right proportions in such a way that the interlocking abilities in the soil is not very good and it is not suitable for compaction. Okay, well graded soil means it has proper percentage of all the particle sizes, which ensures a very good interlocking system, which further is helpful in increasing the strength during compaction and other processes. What is gap graded soil? Gap graded soil means a certain, particle size range. A certain particle size range is absent. Now, if we see the graph, here the x-axis in logarithmic scale has the particle diameter. In this case, it is going from left to right, from highest to smallest size of particles, and the y-axis has the percentage final. So you can see in well-graded soil, this is a graph. The graph is almost, uh, you know, inclined line such that we can see all the particle sizes. If you see here 0.02 mm and approximately over up to 1 mm, all the particle sizes from 0.02 to 1 mm are present. We have the particle size from this to this. If we just draw the line from 0.1 suppose and go here, we will find out the percentage finer, that is the percentage of soil particles finer than that size. Now in the case of poorly graded soil, in this graph we can see it has a almost a straight line up to this. That means from 0.5 to 0.1 we'll find some particles, then 0.1 to 0.2 you see the particles are almost, in a straight line. It has majority of the particles of this particular size. Between 0.1 and 0.2 majority of the particles are from this particular size, and then again 0.2 to 0.5 some particles are present. So this is actually poorly graded soil. This is actually poorly graded soil. Okay. Now what is gap graded soil? You can see there is almost a flat portion. Now what does the flat portion indicate? Here we can see 0.05. If we draw a graph, we can find the percentage finer. And then from 0.1, if we draw the graph, we will find the same percentage finer. That means that particular size between 0.1 to 0.05 is actually absent in that particular soil. Is actually absent in the particular soil. So the graph has become flattened. So in this case, the question was particle size distribution curve with a flat portion represent. The flat portion represents a gap graded soil. Flat portion represents a gap graded soil. Poorly graded soil means too many soil particles of one size. Okay, too many soil particles of one size. Like if we go 80% and we go down, that is too many percentage of soil are found between 0.1 and 0.2 over here. Now in this case, in gap graded soil, a particular soil particle range between 0.1 to 0.05, in this case it is absent, so it is giving the same percentage finer for both the particle diameter. Okay, so this is a graph with a flat portion. It is called the gap graded soil. It is called gap graded soil. Okay. Next question. Soil at the toe of a dam has a void ratio of 0.62. Specific gravity 2.62. Assuming factor of safety of 5, the permissible exit gradient is. Now, for the exit gradient, okay, we need to first find out the critical hydraulic gradient. Why? Because the factor of safety as given is equals to critical hydraulic gradient by the permissible exit gradient. Now in this case, the critical hydraulic gradient, we know IC equals to G minus 1 divided by 1 plus E. Now G is 2.62, so G minus 1 will be 1.62 and E is 0.62, so 1 plus E will be 1.62. So IC will be equals to 1 over here. E is the void ratio. E is the void ratio. Okay, so IC will be equals to 1. Now from here, from this formula, we can see the permissible exit gradient IP will be how much? IC divided by the factor of safety. The factor of safety is F over here. Okay, so IC is 1, F is 5. It will be a value of 0.2. The value will be 0.2. Okay, so the last option is the correct option. So again, in this case, the void ratio is 0.62, the specific gravity is 2.62, and the factor of safety is 5. We are supposed to find out the permissible exit gradient. This is the seepage analysis problem. So the permissible exit gradient has a formula with factor of safety. There is the factor of safety equal to critical hydraulic gradient divided by the permissible exit gradient. Now the critical hydraulic gradient IC is equal to G minus 1 by 1 plus E. G is the specific gravity of the soil solids and E is the void ratio. Now using this formula, we find out that the value of the critical hydraulic gradient is 1, and from the previous formula with factor of safety and IP is the permissible exit gradient, IP equal to the critical hydraulic gradient divided by the factor of safety. Here IC equals to 1, so 1 divided by 5 gives us 0.2. Okay, I hope the solution was clear. Next question. Okay, a sensitive clay has a shear strength of 45 kilonewton per meter square in natural state and 15 kilonewton per meter square in remolded state. The sensitivity of the soil is, so sensitivity, we know sensitivity is equals to we can write as, this is the compressive strength natural by compressive strength remolded. You can also write it like this, Cu natural divided by Cu remolded. What is Cu? Cu is the undrained cohesion. This is also equal to the shear strength. Why? Because from the uniaxial compressive strength and unconfined compressive strength testing, the shear strength is equals to Cu. Why? Why Cu? Because we assume that the soil is having zero friction. It is clay, so friction angle is 0. So the shear strength is equal to the cohesion of the soil mass, and that is equal to half of the unconfined compressive strength based on the graph. This is Cu, this is Qu, and this is the radius. This is Cu. Okay. So in this case, Cu is the shear strength and Cu natural is 45 and remolded is 15. So the sensitivity will be, in this case, sensitivity will be equal to shear strength natural by shear strength remolded, that is 45 by 15. We get 3 as the answer. We get 3 as the answer. Okay. So sensitivity is basically the strength parameter, the ratio of the strength parameters in natural state to the remolded state. Here we can write as the unconfined compressive strength or the undrained cohesion, which is also equal to the shear strength. The shear strength has been given over here as 45 and 15 in natural and remolded states respectively. So using the ratio we can find out the sensitivity of the soil. Okay. Next question. What are the major difference between compaction and consolidation? Compaction, it is the compression of soil by the expulsion of air from the soil. Compaction deals with the expulsion of air, and consolidation is the compression of soil by the expulsion of water from the voids. Consolidation deals with the expulsion of water. Compaction is a very fast process, consolidation is a slow process. Short-term loading is required in compaction, whereas in consolidation, long-term loading is required. The loading can be applied in a dynamic way in compaction because the intensity and frequency of the loading can be changed. Whereas in consolidation, the intensity of the loading should be constant, the frequency also constant. It is a static loading, not changing for a long term. Static constant load for a long term is required for consolidation. Now compaction, it is done purposely before the construction of any structure. Why? To get the maximum dry density. We know after compaction we get a curve showing the moisture content and dry density. We get an inverted curve like this. If you do the standard Proctor test or modified Proctor test, we get moisture content and dry density. This part, this is the OMC, optimum moisture content, and this part, this is the maximum dry density. The soil need to be compacted to maximum dry density before the construction of a structure, and hence the maximum dry density is obtained before the construction of any structure purposely by compaction. But in the case of consolidation, because of the structural load that has been applied in the soil, because the load of the superstructure and the substructure, the load that applies to the soil, that load is a long-term load. Okay, it is a long-term load, and that naturally works over the years to expel out the water from the voids in the soil. So one side we have compaction, which is a fast process. Short-term loading in a dynamic way can be applied and is generally done before the construction process purposely to get the maximum dry density. On the other hand, we have consolidation, which is the expulsion of water from the soil. It is a very slow process with the help of long-term loading, in which the loading is static and constant, and this naturally occurs after any structure is built due to the application of the loads from the superstructure and substructure on the soil. Okay. The basic difference is compaction is the expulsion of air and consolidation is the expulsion of water from the voids. Okay. Next question. If a uniform surcharge of 120 kilonewton per meter square is placed on the backfill with friction angle of 30 degree, the increase in active pressure in kilonewton per meter square is. Now, for the case of active pressure, we first want to determine the coefficient of active work pressure Ka. It is the ratio of 1 minus sine phi divided by 1 plus sine phi. Here phi is 30 degree. Uniform surcharge, that is sigma. It is placed, it is del sigma, suppose. Okay, so Ka is 30 degree, 1 minus sin 30 by 1 plus sin 30, we get 1 by 3. 1 by 3. Now what is the increase in active pressure? We are told to find out the pressure only. Okay, so this is del Pa equals to Ka into del sigma. It will be 1/3 into how much? It is 120. It will give us a value of 40. So, due to a uniform surcharge of 120 kilonewton per meter square placed on the backfill, which has a friction angle of 30 degree, the increase in active pressure will be 40 kilonewton per meter square. Be 40 kilonewton per meter square. I hope it was clear. Next question, the last question. In stability analysis, the term mobilized shear strength is referred to as. The options are shear strength, maximum shear stress, applied shear stress, or none of the above. The answer is applied shear stress. Why? Because if we consider a soil having shear strength of tau f, tau f is the shear strength. Okay, if tau f is the shear strength and the applied shear stress is tau, tau f is the shear strength and the applied shear stress is tau, then we know the factor of safety will be how much? Tau f divided by tau. Now when the factor of safety is more than 1, that means tau f is more than tau. That means a certain part of tau f has been used up to resist the shear stress. So from tau f, tau has been used up to resist tau. So this tau that has been used up from the shear strength, it is called the mobilized shear strength. Now since the mobilized shear strength is used to resist the tau applied shear stress, obviously the mobilized shear strength will be equal to the applied shear stress. So the mobilized shear strength is nothing but the applied shear stress. Okay, I hope the concept is clear. If the entire amount of shear strength is used up, that means the entire shear strength of the soil has been mobilized. That means here tau f will be equals to tau m equals to tau. But in general cases, when the factor of safety is more than 1, that is when tau f is more than tau, a certain percentage of the shear strength from the shear strength of the soil is used up to resist the applied shear stress, and that magnitude, that fraction of shear strength that has been used up, it is termed as the mobilized shear strength, which is equal to the applied shear stress, since it is resisting the applied shear stress. So mobilized shear strength is nothing but the applied shear strength, shear stress. Okay. I hope the concepts were clear. This was the last question. So this brings us to the end of the summary session. So I hope the sessions were helpful for all of you. I have tried to cover as much as possible from all the units, including this summary session, so that you get a brief idea of what has been covered in these 12 live discussion sessions. Thank you, those who have attended the classes. I will stop the meeting now. Thank you.